Welcome back to the finite element class at Universidad de los Andes. We're going to take it from here since the last video, so if you haven't seen the last video, please take a look at that because it's a prerequisite for this one. In this occasion, we're going to talk about the constant strain triangle. So we're going to specialize the 2D elasticity finite element formulation that we developed in the previous video and specialize it to this CST, or constant strain triangle element. So it's called constant strain because what ends up happening is that the main assumption is that within each element the strain is going to be constant, and we're going to see why. Okay, so let's recap a little bit. Let's start by saying, in general, we have that a finite element, and this doesn't matter if you're talking about 2D or 3D. It's going to have a stiffness matrix, a set of element-specific degrees of freedom, and a nodal force vectors. And for 2D elasticity, Ke, the stiffness matrix, is given by the integral over the domain of the element, B transpose Ex, B transpose dx dy, where Ex, the x, it's going to depend on whether you're talking about plane strain situation or a plane stress situation. And the nodal equivalent forces, Fe vector, is given by integral over omega e n transpose b dx dy. So we called the n's the interpolation matrix, and B was the strain displacement matrix. Okay, we're going to give specific expressions for these matrices at this point. So let's start by specializing for the constant strain triangle elements and finding out what N and B are, so we can derive the equations for the stiffness matrix and the equivalent force vector. So we're going to have a triangle. So let's specify this is global xy coordinates, and you have 3 points that define the coordinates, the corners of the node. So this is going to be point 0, 1, and 2. And I start from 0 because the implementation of this is going to be in Python. So it's going to be comfortable if we just have everything in the same notation. Good. So with those 3 points, we define a triangle like this, specified by the corners. So at each corner you're going to have the x, y coordinates of that respective node, like so. And so the interpolation matrix, what it's going to do, it's going to tell you how to interpolate displacement. So let's first define our nodal displacements, as before, to be the ux at node 0, uy at node 0, so this is the x and y displacement at the first node. Then you're going to have ux, oh, this mechanical pencil is really bad, ux1, uy1, and so on, ux2, uy2, okay? So we define the element degrees of freedom vector is going to collect all these values in a column, nice and tidy. This is a 0, this is a 1, ux0, this is ux2. As you follow along with this YouTube lecture, it's important that you write down and you pause this video and you think about all the things I'm talking. So if you need to pause, go back and re-listen to this. This is the advantage we have in the 21st century. Okay, so we define the element degrees of freedom vector. Okay, so this is a subset of the global degrees of freedom. And we're just going to use, if we remember, we're just going to develop one element and then use the direct stiffness matrix, the direct stiffness method to assemble a more complex, larger domain. Anyway, so here we are, and the question of interpolation is as follows. So given the corner degrees of freedom for this node, what is the displacement field at an interior point? So what is ux at this point, y at any given point inside? And that's what the that's what the interpolation matrix is supposed to do. It's supposed to give us, given the degrees of freedom, what is the displacement field inside the element. Okay. So in this case, any, our displacement matrix, is specialized to just the three nodes that we have. So it has that structure. These are zeros. And again, as before, B, the strain displacement matrix, is defined as the derivative in void notation of this element interpolation matrix, and is as follows. So dn0 dx, dn0 dy, dn0 dy, dn0 dx. Again, this is assuming void notation, which is comfortable for implementation later. And here we're going to have dn1 dx, and the structure is going to continue with dn1 dy, dn1 dy, dn1 dx, and the final column over here is going to have dn2 over dx and dn2 over dy. That's the last column. Okay, and remember, if you want to know the strains at a position, that's what you use the strain displacement matrix for. So it gives you interpolation of strains given the nodes, or the nodal degrees of freedom. Great. So what's next? So we have these expressions. This is specialized for three nodes, but we haven't actually given expressions for this. So here comes the tough part. So we have to develop a way to interpolate the displacements into the domain. And here's where so-called triangular coordinates come. So we're going to introduce this concept of triangular coordinates. What are triangular coordinates? So if you have a triangle, of course, like so, what is a set of coordinates? So a set of coordinates, is a way to specify a point in space. So you have x, y, but what x, y are is intersections of x equal constant with y equal constant lines. So in this case, we want to write, or we're going to write a way to specify points in the interior of the domain. And I'm back. So we were talking about triangular coordinates. So again, we intersect two lines or two curves in space to specify a point. So the way we're going to define this is in a way that is independent of what triangle we're talking about. Okay? And that's going to be useful for the developments that we're going to have later. So the way we're going to define this, we're going to define a coordinate denoted by the letters zeta. So zeta 0 is going to be parallel lines to the opposing side, so the side of the triangle that opposes vertex 0. So it's going to be lines that look like this. And they're going to be such that they acquire the value 0 at the edge, and at the node, they acquire the value 1. And points in between just have values between 0 and 1. Okay, so let's specify another coordinate. The coordinate 1 is going to be defined likewise. So we're going to have lines that are parallel to side 0, 2. So they look like this. And they're going to be such that zeta 1 is going to be 1 at the node over there. And at this side, zeta 1 is going to be 0. And you're going to have values in between. And finally, we're going to have a zeta 2 coordinate defined likewise. But this is one of the problems, not a problem, but one of the features of this coordinate system is that the third coordinate is not independent from the first two. Of course, in 2D you can only define independently two coordinates. So zeta 2 is always going to be given by the values of the other one, and is going to be such that basically zeta 0, zeta 1, and zeta 2 all add up to 1. That's the property that they have, and this is easy to prove. Okay, so with that being said, how do you use these to interpolate? So basically what you want is the interpolation to meet the interpolation criterion. So basically, if I'm at point 0 or at vertex 0, I want the value of the displacement field there to be equal to the displacement of the DOF, over the degree of freedom at that point. The same goes for 1. So this gives us a natural way to do that interpolation, and it is as follows. So if I want to interpolate the x displacement field, you do it like so. So ux of the 0 degree of freedom times that triangle coordinate, and we keep going like this. x2, zeta 2. Again, remembering that this the third coordinate is always dependent on the first two. So that's how we interpolate, and this meets exactly that criterion. Points in between are going to be linearly interpolated. If you think about it, these zeta coordinates define planes in 3D space. So if you think about x, y, z, you have a plane that it starts at 0 here, sorry, at 1 here for zeta equals 0, zeta 0, and then drops off to 0 over here and over here. So that defines a plane. And the linear combination of these three planes gives us a linear interpolation of the displacement field. So it's a linear interpolation of the x and y displacement field. Right? So the way to write it down, we write the interpolation matrix like so. So ux, y, so the displacement field is equal to and 0, and 0, and 1, and 1, and 2, and 2, times the whole, I'm not going to write the whole thing, but we have here the nodal degrees of freedom. These are zeros, and of course, it's going to depend on the triangular coordinates. So these are all functions of zeta 0, zeta 1, and zeta 2. Excellent. So with that in mind, the functions, these functions over here are directly zeta 0, zeta 1, zeta 0, zeta 1, zeta 1, zeta 2, zeta 2, like so. So you're going to get the interpolation at the point with zeta coordinates that you want. Okay, let's think about the zeta coordinates a little bit, so to give you an intuition of how they work. If you have a triangle, whatever that triangle is, let's say this is 0, 1, and 2. So this point over here has coordinates 1, 0, 0. This one has 0, 1, 0, and this one has 0, 0, 1. A point that is halfway in this edge is going to be a point such that it intersects this line and this edge over here. So the 2 coordinate of that point is going to be 0 because I'm in the opposing edge. So this one is 0. And the other two are going to be halfway between this edge and this edge. So these two edges define. So it's going to be half and half. Remember, these have to add up to 1. Another special point is the centroid. So that's centroid over there. And that point is a third of the way. So 1/3, 1/3, 1/3. Okay. So that will help you if you think about it a little bit and you try to find out some other points. This will give you an idea of how these triangular coordinates work. Okay, so moving on. In order to write down the B matrix, remember it has this structure: the n naught dx, the n naught dy, the n naught dy, the n naught dx, and so on. The n naughts are the triangular coordinates over here, so I'm going to replace that into this x, 0, 0, dy. So we're going to need the derivatives of the triangular coordinates with respect to the x's. Sorry, this is dz naught over dx, and so on for the other nodes, the same structure. So how do we go about doing that? How do we get these derivatives? So the way we get these derivatives is thinking about how do you interpolate geometry now. So if I know the triangular coordinates of a given point, how do I get the global coordinates of that point? Well, the idea is similar to what we have here. Okay, I can just write x and y, and here I'm going to have the xy coordinates. So basically, the x coordinates of a point, whatever that point is, it's going to be x naught multiplied by the triangular coordinate of that point, x1. So these are the nodal coordinates, right? So the x coordinate of point 0, 1, and 2, and so on. And the same for the y component. So y So I'm just, by the superscript p, I'm just saying this is one specific point frozen in the triangular coordinates. I want to get the xy coordinates of that point given the triangular coordinates and the nodal coordinates. Okay, so that's how that looks like. And I can write this, and we also have the condition that the three triangular coordinates have to add up to 1. So we can write this as a transformation in the following way: x naught, x1, x2, x naught, y naught, y1, y2, 1, 1, 1. And here we're going to have zeta naught, zeta 1, zeta 2. Zeta is the correct Greek pronunciation, by the way. There we go. So this matrix over here, we're going to call it the transformation matrix. It relates the zeta coordinates to the xy coordinates. These are going to be just the triangular coordinates. I wrote a psi, no, this is a zeta, like this. This vector is just, call it x. So basically the xy coordinates of a point, P, are given by this transformation times, which is a function of the triangular coordinates, remember, times the zeta coordinates of that point, and we have the inverse of that. So if you want the zeta coordinates of a point, you can use the inverse transform with the original xy coordinates of the point to get at what you want. Okay, so a little recap, because we've been already 20 minutes or something like that into this video. What are we doing? We're trying to derive the stiffness matrix and the equivalent force vector for a constant strain triangle in the case of 2D elasticity. Okay, so in order to do that, we had to take a little bit of a trip. We defined the element nodal degrees of freedom, so that is the displacement at the nodes of this triangle. We remember what the interpolation matrix is, what the strain displacement matrix is, and we introduced this concept of triangular coordinates, which is a way to move inside a triangle without actually specifying the coordinates, so agnostic to the actual definition of the triangle. And with triangular coordinates, it gives us an easy way to interpolate the displacement field. So that is, given the nodal displacements, specify or interpolate or give us a value of the displacement field inside the element. And then from that, we specify what the interpolation matrix is. And from that, we need to compute these derivatives. So they're going to be the derivatives of zeta with respect to dx. Okay, so this inverse, you can try to do it by yourself by hand, but the expression for it, if you go into a computer algebra system, it's going to be as follows. y1 minus y2, y2 minus y0, y0 minus y1. This is a horrible y, let me fix that. And x2 minus x1, x0 minus x2, x1 minus x naught, x1 y2, x2 y1, x2 y naught, x naught y2, x naught y1, x1 y naught. So that's the inverse of the T matrix. And now this 2A product is simply the determinant of that matrix. So it's x naught y1 minus y2 minus x1 y0 minus y2 minus or plus x2. There we go. So now we have this matrix gives us the zeta coordinates given the xy coordinates of a point. So here's a little trick you can use to find out whether a point is inside the triangle. Just specify the coordinates, evaluate the inverse matrix, and specify what the coordinates are in xy coordinates, and evaluate this. And if any of these triangular coordinates comes outside the 0, 1 interval, that means the point is outside the triangle. Anyway, so if we want to do derivatives of this, so remember we need to compute the d zeta to x and d zeta to y. So if we want to do d zeta, we can grab this over dx. So you're going to get all of these the differentials with respect to x. So let's do d zeta 0 over dx, blah blah, d zeta 2 dx, like so. And here we're going to have t to the minus 1 plus the derivative of this with respect to x. That's going to be 1, 0, 0. So this is going to give us basically the first column of this matrix. So it's going to be 1 over 2a, y1 minus y2, y2 minus y naught, y0 minus y1. So on and so forth for the derivative with respect to y. It's going to give it that second column. So that's great. We have these derivatives. So now we can write what the B matrix is. So we have N matrix. We have the B matrix. The superscript E refers to the number of the elements. So the elements are going to have a number within the domain, and that's just a way of keeping track of what element it is inside the domain. So now what? One thing you can notice is that, these, let's say, d zeta 0 to dx was 1 over 2a, and y1 minus y2. And one thing you can see is that this derivative is not a function of zeta. So it's not a function of zeta 0, zeta 1, zeta 2. Thus, it's not going to be a function of x, y, z. Just a function of the area of the triangle and the corners of the triangle. So that's cool, because when we compute the stiffness matrix, it's going to be the integral over the element domain, where the element domain is just the triangle of B transpose EB dx dy. And now these B matrices do not depend on the position inside the element. Therefore, I can bring them out of the integral like so. And this is just the area of the element. So this is area, which is the same area we have up there. So the stiffness matrix of the constant strain triangle is this expression, which is the only element that has a closed form or a nice closed form solution for its stiffness matrix. Now let's do the FE vector. The FE vector is the integral over omega E and transpose B dx dy. And this is going to be easy to do. This is going to be sigma E, and we're going to have the zeta functions like so. Let's extend that bracket. The off-diagonal terms are all 0. Bx, by. Remember, these are body forces. So body force in the x direction, body force in the y direction. Dx, dy. And let's think about these functions a little bit. And imagine I have 0, 1, and 2. And I'm looking at this in a side view where I have the x and the y coordinate and zeta 0 upwards. So the way that looks is at the 0 node, that's going to be 1, and at this edge it's going to be 2. So it's a plane that looks like this. Is that wedge. Now the volume of that wedge, so basically the integral over omega E of zeta 0 dx dy is going to be the area of the triangle multiplied by 1/3. So AE over 3. That's basic geometry. So that means the bx, by, these don't depend on the xy coordinates, so I can take them out of the integral. And these are all going to evaluate to 1/3 integrating over. So FE is just the area of the element over 3 times this matrix. Let's put the zeros there for reference. Times bx, by. And with those two matrices, the stiffness matrix over here, given the EX, so whether it's plane strain or plane stress, and the FE, we are ready to use this element in a finite element setting. So this is the formulation of the constant strain triangle. It does have a constant strain inside, so that means that the stress is also constant inside this triangle. We're going to see that results in poor convergence properties, but this element is so simple that it still gets a lot of attention from researchers. It's easy to implement, and you can just have many of them, and many people go for that. Okay, this has been it for now. Next up, we're gonna see how to develop the 4-node quadrilateral element, and we're gonna do some implementation in Python. Thank you.